visualize latent space. Okay, if you take a look at the Google, okay, you can simply just Google latent space. For example, I think the topic we talked about is NIST, which is handwriting digit, right? And you can see that there are a lot of figures when we talk about latent space. So latent space is right here. Again, we have origin space. You have x1, x2, and maybe you have another even more dimensions right here. And we have latent space, right? Again, you have k1, k2, and maybe even more dimension right here, okay? So originally, the data point, they should be somewhere in the original data, right? In the original space. It is a handwriting digit, so there will be that many dimensions. What if we make a autoencoder and make it, I say, 30 dimension? So there will be K1 to K30, right? So handwriting might look like this. K1 maybe it represents a digit. So we have a 1 right here. That's many pixels, and it's right as 0. What is the original space stands for? They are pixels, right? So they are either black or white or some grayscale color between 0 and 1. So view it as, okay, that is 1.0 and that is 0.0. So this is a grayscale of the first pixel. So basically, if you take a look at P2 right here, okay, and of course there are some other dimensions. The projection of the first axis, which is x1, which is the very first pixel of this image, handwrite image, okay, it has a color, grayscale color between 1 to 0. Do you think that, for example, P4, some P4 right here, P4 and P2 are so close? That is because their first pixel, which is the first dimension x1, they maybe, okay, they have the same grayscale color. But is that truly represent P2 and P4 is the same digit? For example, 1 or 2 or 3? No, the answer is no. 假设在原空间里面呢，因为这个原本是这个 x1 到 x700多维嘛 ，x1 表示第一个 pixel 的值嘛，应该是接下来的那一支箭，它是一个 grayscale 的颜色。然后 P2 假设 project 到 x1 的时候，表示说第一个 pixel 是这个颜色的，比如说这可能是 0.85 吧，哈。那假设有另外一个值啊 ，P4 在它旁边，它也 project 到同一个点上，在 x1 这个轴上，那就表示说它的第一个 pixel 也差不多是那个颜色。那问题是，在这个700多维空间里面 ，P4 跟 P2 在第一轴上很接近这件事情，有 infer 它们两个是同一个数字吗？没有吧，对不对？实际上是没有的嘛，对不对？它只是在700多维空间里面的两个点，它刚好在这个维上很相近，对不对？好，那我们不是要说做一个 autoencoder 嘛，对不对？那这 autoencoder 很多形式嘛，那我们常用，因为这是图片嘛，对不对？所以呢 autoencoder 里面可能是用 CNN 做的，就那 encoder 里面是用 CNN 做的，好，所以它就能够很适切把一些 local 的 information 啊，比如说点附近的像素的颜色啊，把它想办法把资料凑在一起。然后最后生成一个 K， 然后 K 就到右边去。那右边这个 K 实际上是一个综合整理嘛，就是前面那些这么多700多维里面，然后我有 local 的 information 被 CNN 跟 Maxport 抽出来之后，然后形成一个30维的 K。那在这30维的 K 里面呢，我们就比较有理由相信，好，一样的哈。假设这里有个 P2 好了 ，P2， 我们就有比较理由相信啊，如果 P2 跟 P4 它的整个 image 比较像的话。他们在新的这个30维空间里面，他们应该就会在附近。你要记住，在原空间里面 ，P2 跟 P4 在第一维度像的意思是，他们第一个 pixel 颜色是不是很像的？但这件事情对于判断，比如说我随便跟你讲，有两个 image， 它的第543维的那个颜色很像啊，就开始想543维是在这 image 哪里呀？那它如果是黑色，它到底是5的凸出来的地方，还是4凹进去的地方？这件事情根本就不 make sense， 对不对？所以如果那个 autoencoder 做得很好的话，我们在右边做这个判断会比较好一点。所以右边那个判断意思是说，现在有30维嘛，30维里面第一维是什么？30维里面的第一维应该是，如果前面是 CNN 的话，比如说 CNN 有一个对 local information 的分片跟看法，而它那个看法呢，吸收整个748维里面的 information 之后，得到30个维度里面的 第一个观点，他认为 P2 跟 P4， 如果这个第一个观点30个观点里面第一个观点如果是很像的话，那他们的第一维度就会在负。那它第一个观点很像，第二个观点很像，第三个观点很像，一直到第30个观点都很像的话，表示他们几乎就是同样数字的那个图样啊，对不对？这个是一个解释了啊，我跟你讲遍啊。So here's the explanation. In the original space, if as we know, the x1 is the pixel, the color or the grayscale color of the pixel, the very first pixel of two images, for example, P2 and P4. If they have the same value, it just indicates that the very first pixel of P2 and P4 have the same color, but it does not indicate they are the same digit number, handwriting digit numbers, because they're just a pixel with the same numbers. However, the right-hand side, which is a little bit different. For example, if I use convolutional neural network, for example, I use convolutional neural network to create an encoder to compress the original information from 184 dimension to a 30 dimension. That means I have 30 different point of view to review all the information received from the 748, 84 dimensions, those information. And I use CNN, which means I focus on local information around those pixels. And I have several different kernels, several different filters to look different patterns among the entire data. So at the end, I have 30 different point of view to describe the original data. Okay, so at the right hand side, if P2 is right here, again, if P2 is right here, maybe I should say P2 prime, okay? Maybe P2 prime is right here. If P4 prime is close to P2 prime in the Latent space, that means for the very first point of view, which is K1, they are almost similar, which means maybe they have a shape, straight line at the top of the pixel. Okay, they are the same. For example, the second point of view, maybe there is a curve. Maybe there is a curve at the bottom of the image. So there are several different point of view. There are 30s of them. Okay, so at in the Latent space, if the P2 prime, P4 prime, they are really, really close. That means they have 30 different point of view, and most of them are very similar, and that indicates they might be the same digit in the Latent space. So when we do clustering in the Latent space, that will be much, much better than do clustering in the original space. As I mentioned before, if you Google Latent space and NIST, you will figure out some figure like this. We can see that very carefully, okay? We can see that, so that is basically Latent space. However, those Latent space, as I mentioned before, Latent space should be like 30 dimensions, 50 dimensions, 100 dimensions. But we put, I mean the people who create this kind of figure, they plot that in a 2-dimension surface, right? In a 2-dimension surface, for example, 2-dimension space. So basically, after they obtain the 30-dimension information right here, if you want to plot a figure like this, then the most convenient way, simple way, is you do principal component analysis on this 30 dimension, so that you can decrease the dimension from 30 to only 2, right? Of course, you will lose a lot of information when you do such kind of dimension reduction by using PCA. However, if you have only 2 dimensions, then you can draw. I should say it's PC1 and PCA1. Okay. If you further do something like that, x, right, k, x prime, and you further do some PCA to become k equals to 2, then you can plot the Latent space, and we have another Latent space, but it has only 2 dimensions, so then you can draw this figure. So that, okay, there are several data points. For example, there are 1 data point right here, okay, that is, of course, it has 2 values right here, that is PC1, PC2. Of course, you can reverse it, okay, to figure out, okay, where is the original data point, which is 30 dimensions in the Latent space. and you can map it back to x or x prime to see, okay, that label, that data, it is original, it should be 8, right? It should be 8. So for example, if you have an n data, and you have a lot of 1s, a lot of 2s, and a lot of 0s, and a lot of 9s, and it's right here, the n data right here. You pass through those n data to the encoder that you train, and then you get the Latent space information of the n data, right? And you pass through those Latent space data with 30 dimension to another dimension reduction tool, for example PCA, to make it be 2 dimension, and then you can draw this information, right? So that is exactly the same. Okay, usually we have 2 dimension, right? So PC1 and PC2, and you can draw this. So you have n data. You can pass through the encoder and the principal component to find the position, which position is right here, right? To find the position of this image in the PCA Latent space, right? You may figure out some space right here, for example, right here. In the Latent space or in the PCA Latent space, there's always some place which that after your encoding, after your principal component analysis, you map them to this surface. There's always some space which is empty, which means you don't have any data, which original data can be mapped to this space, which is empty. In this area, most of the data points in this area, okay, they are clustered, right? They looks like a cluster. They are originally ones. 好，就是我们会在这个我们讲嘛，我们过这个 autoencoder 只会得到一个 k 维的 Latent space 嘛。那因为我们硬要画图嘛，对不对？其实 k 维是可以画出来的，只是因为我们现在硬要画一个图在2D 平面上，所以我们可以让它过一个 PCA， 让它强制降回到2维，啊，所以我们就会有一个2维的坐标。那以这个像那个8的那个例子来说，那就是你把原来的8嘛，原来的8应该是784维的一个值嘛，那784我们根本没有办法想象啊，对不对？所以我们就先让它过autoencoder，啊，出来是30维，因为30维我们也没有办法想象啊，所以我们就硬打过一个 PCA， 它就得到一个2维的数字。那我们就把这个8这个小小的这个点在这个2维的 PCA 的这个平面上面去，然后我们不是用 n 个资料吗？我们就把 n 个资料全部都做一样的事情，然后就会得到这个图嘛。然后发现这个图里面有很多空白的地方，这个空白的地方表示说原始的资料并没有描述这个 Latent space 的空间里面这些空的地方是什么东西，我们并没有描述它是什么，好吗？比如说原始的资料在这边是不 work 的，那就跟我们刚刚在解释那个等高线那件事一样啊。实际上啊，你现在看到的是这个范围，对不对？在这个范围的更外圈的地方啊，就是更外面的地方啊，根本就没有资料点啊，根本就没有资料点，对不对？所以那个有点像是什么呢？有点像是，如果啊，我们现在是辨识手写数字嘛，对不对？好啊，那如果你拿一个一样是28×28维的这个手写的资料，它里面写什么呢？里面写英文字母 S 好了 ，S 这个字在原本的手写资料里面是不存在的嘛，可是 S 是可以写出来的嘛，因为那个700多维里面你还是可以点出一个 S 的形状的样子，对不对？然后我们之前不是说了吗？这 S 的值根本就不在这个所谓的潜在空间的这个比较密集的这个范围里面，它有可能那个 S 的值啊，就会落在你现在眼睛看到这个黑色圈圈的外面，对不对？因为你根本就不知道它是什么。那很有可能有另外一种情况是，那个 S 啊会落在你现在看到这个紫色的这个空白的区域里面。因为什么呢？因为 S 可能长得有点像8，然后又长得有点像9。所以它会落在你用眼睛认真看8在哪里？8是不是在这个图大概正中间的地方？啊，9呢？9在哪里啊？9在8的左边有一些人，然后在9的在4的上面有一些人，对不对？好，那现在8跟4中间是不是有一个紫色的圈圈？我先讲是这一块地方，那 S 可能就会掉到这一块地方去，因为 S 长得像8也长得像9。当然这是用猜的啦，就是实际上你可以真的试试看，把一个 S 丢进去，它可能会在这个 PCA 的平面的某个地方会有个落脚的点。那就回到我们刚刚前面讲的，只要没有落在这个区域里面，就是空的地方，或者它附近旁边没有人，或者说它落在这 这个黑色范围的更外面地方，我们都可以视为是这个资料我根本过去就没看过，所以就可以做 anomaly detection， 或者是说，对它在这个潜在空间里面呢，它夹在已知的资料的中间的空白地方，所以是我没有看过的东西，我可以视为它是某些东西的奇怪的合成的样子，像 S， 它可能就长像8的长相，好吗？这个概念都要记得，因为我们做的是一个连续空间的 mapping， 只是这个连续空间里面目前被形塑出来的样子，如果硬把它弄成2维的话，它长得是你现在眼睛看的这个样子，中间其实有很多空洞的。那些空洞是什么呢？其实我们不知道。好，所以我们有另外一个方式是这样子：假设你想知道那个空洞是什么，那怎么办？我现在这边紫色不是有个叉叉吗？对不对？啊，这个值是什么？这个值是 PCA 的值，2维的值。PCA 可不可以做反推？可以，因为那个 PCA 的公式我们不是都有吗？你就反推回去那个 K 的空间。啊 ，K 的空间可不可以反推回去 X？ 可以，因为你有公式，就反推回去。所以你可以随便的在 Latent Space 里面，或是 PCA 的 Latent Space 里面，随便的就找一个点，然后想办法把它反推回去到原本的784维。那它就有784个数字介要跟你之间，你还是可以把它画成一张图的样子，对不对？那个图会怎么样？就会很奇怪。如果以我们现在画的叉叉这个点来说的话，它会长得有点像8，又长得有点像4，右边什么？它右边是6嘛，它又长得有点像6。它会是一个奇怪你没有看过的东西，然后是它附近的东西的一个混合体，因为我们说那个空间的 mapping 是连续，所以它就会生成下面这张图，对吗？它是不是长得有点像8，又长得有点像4啊？4在哪里？4在左上角，是不是？它跟4跟9，它会介在4跟9跟8的中间，对不对？那9是大概在这一块，4模糊4在这一块，8是大概在8很大的，9也很大啊。9大概在这一块，对不对？然后8是不是大概在8大概在这一块？所以你随便的在 Latent Space 里面随便点一个点，如果你都可以回推回去原本的维度，那它是谁呢？它很有可能就是它了。一个4不像的东西，有点像8，有点像9，有点像4，可以吗？可以理解这件事情吗？好，我英文再讲一遍哈。So let's take a look at this thing, this figure. You can see that there will be a lot of empty space in the Latent Space, which is not described by the original data point. Take this cross, for example. This Latent Space has no information, right? Because this does not map any original data point. Since we have this figure, right? We know how to map X, which is 784 dimension, to a 30 dimension, 84 to a 30 dimension Latent Space, and to a 2-dimension PCA Latent Space. Right? So basically, we can randomly select any data point in the PCA Latent Space or in the 3-dimension Latent Space, and we can map this data point back to the Latent Space or back to the original space. So that for this data point, for this purple data point, right here, it is somewhere around 8, 4, or 6, or 9, something like that. Right here, and come back to the Latent Space and come back to the original space. So for this data point, go back to the original 784 data point. So we can draw a new figure, which has 784. Usually we will get something like that. That is the area around the true 8. Here is the 9, right? Maybe there is 4, okay? So maybe the X will be mapped to somewhere between 8 and 9. And we can see it is a very strange thing right there. It looks like 8, sometimes looks like 9, sometimes looks like 3 or something like that. So basically, you create a new data point. You can find some cluster in the Latent Space, right? And you randomly simply just select a data point in the Latent Space. And it can be mapped back to somewhere you don't know. And maybe that is meaningless in the original data space. And usually it is meaningless. Okay? We can use such kind of things to do anomaly detections. And one of the important applications of Latent Space is to create new images. What does that mean? Neural network. So here's an application. Okay, you can simply just random use, for example, neural network, latent space, and some famous painters name. We can build up autoencoder. Okay, by using those very famous paintings. 好，中文这两个，我们可以建一个 autoencoder， 对不对？然后它的 autoencoder 不是这么烂手写数字啊，我们就随便找一些非常有名的，比如说梵谷或是毕卡索的100幅画或是1000幅画，所以他要做的 work 也很简单嘛，把那比如说把那100幅画一样啊，一个 pixel 一个 pixel 把它建起来，然后你做一个 autoencoder 啊，中间用 CNN， 然后再把它还原。所以那个中间的 latent space 是什么？中间的 latent space 就是一个 representation of 你看你输入的画的样子。所以我们会把所有的梵谷画全部都丢进去，然后用它做一个 latent space。然后这个 latent space 很厉害，它可以做什么？它可以还原梵谷的画，对不对？比如说原本梵谷画一样是700多维，你中间用的 latent space 假设也是30维好了，当然它 x prime 也是700多维，你是不是就可以还原一个梵谷的画？当然我们做画的时候，那个维度会比较高啊，因为那个画的解析度会很高。比如说一个1000 pixel 乘1000 pixel 的数位的梵谷的画，那这样可能就是要100万个 neuron 才有办法描述它的。那中间可能就维度你可能就不能太小，30维显然太小啊，你可能用那个几万维的 latent space 来表示梵谷的画。所以中间那个 latent space 表示是 represent 梵谷的画的一个潜在空间，中文是这样子翻译的。然后你就发现什么呢？这个潜在空间啊，跟我们刚刚看数字一样，有很多的洞洞。那些洞洞表示什么东西？那些洞洞表示梵谷没有画出来的画，但是我们可以随机的在里面找一些 latent space 的空间，然后想办法再把它 match 回去成 map 回去成1000维乘1000维，你就得到另外一张画了。另外那张画，这张画有什么特性？它可以经由梵谷的那个位置，就是我们这个潜在空间的位置 ，map 到中间很好的梵谷的 representation， 然后很好的又可以再被还原。当然我这样讲已经过度的简化了哈，就是实际上有些其他的事情在做这件事情，所以有很多的所谓的生成模型，就是 generation 的 model， 都是利用潜在空间的这一个很特别的特性，就是那个潜在空间里面有很多空洞的地方，那些空洞的地方是我们在原本的资料集里面没有看过的。可是潜在空间既然能够很顺畅的能够表示一个原空间的东西，然后有 W 跟 W prime 可以做这个encoding 跟 decoding， 就是能够做还原、压缩跟还原，那表示这个潜在空间那些 W 很厉害，他一定学到了什么梵谷的东西，或者学到了什么东西，所以那些潜在空间里面的空格呢，就很有这些实用价值。你不要以为它只是 anomaly 而已，它可能就是一幅梵谷过去没有画出来过的画，然后在潜在空间里面的某个点，你就把它回推回去，它就会长得很像梵谷的画。当然这个已经过度简化，你们有兴趣的话可以找那个所谓的画的生成，它里面就是会含有一些潜在空间的概念在里面。这个我们可能要到期末的时候才会有机会讲，好吗？好，我英文再讲一遍咯。Okay, I would like to show you an example of this latent vector. So you can simply just Google latent space, neural network, convolution, and some very famous painters' name. Okay, then they will show you some example of how do we use latent space to create new paintings that have never painted by that painter before. As we mentioned before, there will be a lot of empty space in the latent space, right? You can find, for example, Van Gogh's 1000 or 100 paintings. So basically, you can use a lot of Van Gogh's paintings and feed them into a autoencoder. Okay. However, the autoencoder might be a little bit larger. For example, that it can be 1000 by 1000 pixels, and hidden layers, which is the latent space, could be maybe I say 500 dimensions or 300 dimensions, which should be larger than the dimension you use in handwriting autoencoder. Okay, so basically when you do such kind of things, you will come up exactly this figure like this. Every data point represents one of the paintings painted by Van Gogh, right? However, there should be some empty space in your latent space, right? Such like this. So basically, you can create a new paintings by randomly select a point in this lens space, then back to the original 1000 by 1000 pixel. And that will create a new paintings. And this kind of painting, because we have those weights, we have those kind of dimension reduction mechanisms. Those weights learns how to map Van Gogh's paintings from a higher dimension to a lower dimension, which is lens space, right? So basically, when you do such kind of reverse, we call generation, okay? You can generate new paintings along with those weights. And as I mentioned, those weights can mimic Van Gogh's painting, his style, and the way he described objects. So basically, you randomly select one data point in the empty space. You can map it back to a original 1000 by 1000 space, and it creates a new paintings, which will be very, very similar to Van Gogh's painting style, something like that. Of course, that is an oversimplified explanation of painting generation. There are a lot of different and more complex structures, neural network structure, to create such kind of paintings. Okay, so that's one of the important application by using the concept of random space. Oh, I think that is a very nice figure right here. After we do the autoencoder, after we learn how Van Gogh's painting style by using autoencoder, we can even design a neural network to ask the neural network, you can paint this cat by using Van Gogh's painting style. Okay, of course, this is much more complex. So if you're interested in these things, you may take a look at just Google it. Okay, some of the articles will explain how to use lens space to create such kind of new paintings.